One, I promise this is going to be quick and easy. All right, so inductive reasoning and conjecture. All right, so look like difficult terminology. It's not, okay? Conjecture is just an educated guess. There's not supposed to be an and, it's supposed to be an educated guess. So, so an educated guess generally looks for patterns, okay? So like, let's say you drive to school and you leave at 8 o'clock in the morning and it takes you 17 minutes one day, the next day it takes you 18 minutes, the next day it takes you 17 minutes. What's the conjecture about how long it takes you to get to school? Somewhere around 17 or 18 minutes, right? Now there could be traffic, there could be other things, okay?
Could you also look at our plot?
Yeah. Okay, inductive reasoning is basically using those examples to arrive at a prediction. So that's when we use those patterns to make a conjecture, okay? All right. So inductive reasoning, basically looking for a pattern to make a prediction or to make a conjecture. Okay, so conjecture is making that educated guess, and the inductive reasoning is looking at patterns that will help us make that conjecture.
So it's exactly what Samantha said. I didn't say anything.
We will do the part with hypothesis conclusion. That's going to be the next lesson. So all we're doing in this lesson is making conjecture. Okay. Eric was driving his friends to school when his car suddenly stopped 2 blocks away from school. So make a list of conjectures as to why his car stopped. Okay, but like, what would be an educated guess? Why would your car stop? Ran out of gas.
Flat tire.
Maybe it was an old car and it broke down.
Old car.
With a line over it.
Stolen.
Broke down.
He fell asleep.
I heard someone else said a flat tire.
Or maybe he just put his foot on the brake.
Had an accident.
Foot on the brake.
Ran out of gas.
Okay. So all of these are conjectures. Now, we don't have a way of knowing what the actual reason why it broke down unless we have more information, right? So generally speaking, in geometry, we're going to have more information. So, for example,
Then why did we do that?
okay, it's just to practice making conjectures about what could have happened, right? Okay, maybe there was traffic, right? There could be a whole bunch of different reasons. These are just the practice. Suddenly stopped. Well, a car could have stopped in front of him, right? So let's look at a mathematical conjecture. These are what we call triangular numbers. So it's basically 1 dot, then we make a triangle out of 3 dots, then we do another series, like another layer of dots, if you will. There's 6. Add another layer, you get 10. So we want to look at what would be a conjecture without actually drawing it out. What would be the next number? 21?
Why would it be 21?
Okay, let's see. Sure.
Because from 9 to 1 to 2, it's 1 to 3, sorry, it's plus 2, and then 3 to 6, plus 3, 6
Yeah, it's 21.
plus 4, 10 to 5, plus 5, 15. It should be an honors. I agree, you should be.
Okay. So we're looking for what's the pattern? How are we getting from one number to the next? So that's a great way of looking at it. Now, what anybody else look at? What would happen if I added another layer to this? You would add 6 more because, right, this bottom, look at the bottom rows. 1, 2, 3, 4, 5. So if I took this and added 6 more, that's another way. So actually looking at the shape. Both are correct. Okay?
Wait, what's another one?
Do you see how, like, the bottom row, like if I just added 3 more, I'd get this next one. And then if I added 4 more to the bottom, and then if I added 6 more, so on.
The whole lesson?
let's make a conjecture about the next item in the sequence. Okay, so my conjecture, again, we're just looking for a pattern. Now this time, it's not going to be adding the same thing. It's not going to be subtracting the same thing. It looks like multiplying or dividing. It's dividing by, so if I look at divide by 3, and then I divide by 3 again, that will give me 100. So then if I divide by 3 again, is that going to give me a whole number? No. So I'm just going to write 100 over 3. Now, if you wrote 33 and 1/3, isn't that the same thing? That's fine. Or if you put 0.3 or 33.3 repeating, that's fine, but we don't usually do the repeating sign anymore. It's better just to leave it like that. Okay, how about the next one? Anybody see the pattern?
Oh, you divide. No, oh yeah.
It's multiplying by
4 times.
Let's see. This one is multiplying by 2. And then how do we get from 4 to 12? Times 3.
times 4.
Now you see the pattern. So times, whoops, not plus, times 5. Times 6. Looks like we need a calculator for our conjecture.
10,080.
10,080. Okay. So that's your conjecture part. We've looked at number sequences before, probably in like pre-algebra, I'm guessing. Okay. Okay.
Wait.
Probably usually do it before algebra, or it's grade 7 math. It depends on where you. Yeah. Okay, counterexample. Okay, these conjectures.
See, in 8th grade, we retook transition math, but they renamed it pre-algebra.
Okay, counterexample. A conjecture based on several observations may be true, but false in others. It only takes one false example, that's a counterexample, to show that a conjecture is not true. Okay, so in order for a conjecture to be true, it must be true in all cases.
So is it based on one false example?
It's one false example. So you can write this out in detailed words, or you can make a detailed drawing. What's that?
Wait, so what was the definition?
The definition, counterexample, it would basically be a counterexample is one false example to show a conjecture is not true. Okay, well, we'll see in this first example here. Okay, so here's what we want. We want the first part must be true. Okay, so I'm going to have a given statement where that must be true. What we want to determine is whether the conjecture is going to be true or false. Give a counterexample for any false conjecture. So the question we're asking ourselves, must this be true? That's our question. Okay. So angle 1 and angle 2 are supplementary angles. Okay, so I need to have two angles that are supplementary angles. The conjecture is angle 1 and angle 2 are both right angles. Does that have to be true?
Yeah.
Yeah. Well, no, but it is.
Okay, could this be true?
Yeah.
Does it have to be true? No. Okay, so since this does not have to be true,
Wait, how does it not have to be two right angles?
okay, what does supplementary mean? You have two angles that add up to what?
180.
180.
And now you can find yourself.
Okay, so
No.
It's
Oops.
90 and 90.
Okay, but can I draw a picture of two angles that are supplementary, but they're not right angles?
Yeah.
That's your counterexample.
So you're just finding stuff to make it not.
Exactly.
It's like what my sister does.
What's his name? That guy?
He's not. Is he available during lunch?
Yes. Okay, here's what I'm going to do. I'm going to draw a picture. I'm going to make a linear pair. Do you remember linear pair from chapter 1? It's two angles that form a line, and they also add up to 180. Okay, now, this is not enough because I need to make sure that I have a detailed drawing. Now, it looks detailed, but what I need to do is I'm going to put an angle 1 and an angle 2, because remember, this was referring to angles 1 and 2.
You have to put a degree.
And then let's put some degrees in. What do I specifically want? I want two angles that add up to 180, but I don't want them to be right angles. So what would be two angles that add up to 180? 150 and 30, what were you going to say? Yeah. So I'm going to put 150 degrees here.
I drank a liter of water on the way. She actually did.
Okay. So did we draw a counterexample? Do we have the first part? Is that true? Are angles 1 and angle 2 supplementary? Yes. Did we draw two right angles? No. So that's how I know I have a counterexample. I basically drew two different angles that add up to 180, but they don't have to be right angles. Yeah, Leo.
So are you trying to prove that the second statement is like always wrong?
Right. It's like weird to think about it that way because you're like, but that can be true. Doesn't matter if it can be true. Does it have to be true?
So you need to find another solution to that?
Yep. Okay, let's look at the next one. Points A, B, and C are collinear. Okay, so that has to be true. The conjecture is, does B have to be between
No.
A and C?
Because you could just write C, B, and A.
Okay, so my counterexample. So this is false. So let's draw a picture. Now you could also write it out in words, but it's so much faster just to draw a picture. So you could write you could write A could be between B and C. So basically what Max was saying is you could have
C, A, B.
CAB.
I did BAC.
Just B can't be.
Right. So did I draw the given true? Are points A, B, and C collinear? Are they all on the same line? Yes. Did I have B between A and C?
No.
No. So I drew a good counterexample there. This is the last one. N is a negative number. My conjecture is n squared is a non-negative number.
True.
Is that true in every case?
No, because, wait.
If I have a negative
You have a
number,
negative number, you square it, you
Oh, yeah.
multiply by itself. It's a negative times a negative. It's a positive.
mhm.
So it's always true. That's
Yeah, so
why-
even if it's a fraction, right, and I square it, I still get a positive, I get a non-negative
So you
number,
can't make
right?
that one.
So it's true. Now, if there's true, I don't have to write a counterexample. So there's no counterexample.
You just write true.
You just write true.